Yeah?
Okay.
Okay. So welcome back again.
Okay, yeah, we're good.
Great. We are not hearing from David Ayala, as probably most of you know. We will hear from him, I think, tomorrow. Instead, I'm delighted to introduce Ben Antieau from Northwestern University, who will tell us about the K-theory of cyclic groups. Thanks, Ben.
Thanks. Thanks. It's a pleasure to be here. First time simultaneously being on two continents. I guess I'm not David. I think David is running here, but I hadn't realized Canada was so large. So I guess he'll be here just in a couple more hours. So today I'm going to tell you about joint work. So this is a project called the K-theory of Z mod P to the N. It'll be about some rings a bit more general, and everything I'm going to say is joint with Achim Krause and Thomas Nikolaus, and builds on the work of many, many other people. So I understand I can't write too low on this board, so let me just start here. Our main theorem is that there's an algorithm to compute any individual K group, Kr, of OK mod pi to the n. Here, so this is for any R and Z. OK, let me introduce some notation now. Is it a problem if I kind of have it in the middle? No. So OK, so K is a finite extension of QP. So it's a Piatic field. OK is the ring of integers. Pi is a uniformizer. And let me just fix a couple other bits of information. OK mod pi itself is a finite field. That's FQ. And Q is some power of P. That power is going to be called F. E is the ramification index. And it has the property that this number, D, the degree of the extension, is P times F, is E times F. Okay, so we're interested in the K-theory of quotients of discrete valuation rings of this form. And the statement of the theorem is that there's an algorithm to compute those groups. So it's a finite, these will be finite abelian groups in all cases. And there's an algorithm, and we've actually implemented that algorithm to compute this in any given range, at least if you have enough computer power. Okay. So more specifically, let me say a little bit more about how this works. And the goal today is going to be to give you as complete a picture as possible of how we do this. So I'm going to minimize historical comments in this talk and try to talk as much as possible about the math. So specifically, oh yeah, and one more piece of notation here. Let's let W be the ring of p-typical Witt vectors of FQ itself. So that's the ring of integers in the maximal unramified subextension here. So more specifically, what we do there is a specific complex. There's a cochain complex for I at least one of the form W, so this ring of Witt vectors, to the in minus 1, W to the 2 in minus 1, W to the in minus 1. N is the power of the uniformizer that we're killing. Thanks. That'll be fixed throughout the talk. So there's a specific cochain complex. Now these maps are not W linear, so I'm going to rewrite this as ZP to the F times IN minus 1, because this is a free module of rank F over W, right, where F is the power of P appearing in the size of the residue field. ZP to F IN minus 1, ZP F IN minus 1. And now these maps are ZP linear. There's not a lot of choice there. We'll call those sin 0 and sin 1. And I'll call this complex CI bullet. These are in cohomology. I'm thinking of this cohomologically, and these are in degrees 0, 1, and 2. And the main, the real content of the theorem is that CI bullet is equivalent to to what's called the Piatic Syntamic Homology. Okay, which I'll define a little bit later. And as the result of work of Bott, Morrow, and Schulze, this Piatic Syntamic homology is closely related to topological cyclic homology, and that's closely related to algebraic K-theory. So in this case, what that gives us is that the 2I minus first K group of OK mod pi to the n with ZP coefficients. So we're going to look first at the P complete part of this. So this is just isomorphic to H1 of this specific complex, CI bullet for I at least 1, and K2I minus 2 is isomorphic to H2 CI bullet for I at least 2. When I is 1, then this would be about K0, which we know everything we want to know about. So that's a little bit less crucial thing to think about. And so that's the main theorem. The main theorem is that we can that there's a specific 3-term cochain complex like this, which computes the K theory. And the real content of the theorem is that we can fill these are matrices, right? These are maps between free modules of finite rank over Z piatically free modules. And so the real content of the theorem is that we can take these matrices and fill them with actual piatic numbers and then compute the homology or cohomology of this matrix. Okay. The last part is easy using computer algebra systems. R was just a degree. I'm saying we can compute it for any given degree R. Here I'm saying what we really do is compute this complex, and we can do it for 2 R's at a time. These are sort of, this is basically what's coming out of some kind of motivic filtration. And that motivic filtration isn't so interesting in this case. Some spectral sequence collapses and there are no extension problems. And so we can basically read off K groups directly from the graded pieces. Any other questions?
Yes, when you think you can compute the Piatic numbers, you mean you can compute arbitrarily good approximations of the Piatic numbers?
Yeah, sure. We can work with finite precision, and we can pre-compute a bit what that finite precision is needed for our specific problem, and then you know to compute. We also have a priori bounds on the sizes of the homology groups, so you don't need to You can fix the Piatic precision at the beginning. Well, it's the P complete K. Oh, I'm sorry. Thank you. The first question was about Piatic precision, and the answer was there's no problem with Piatic precision. We can figure out what we need beforehand. The second question was what? Oh, okay, and that's, you take the K-theory spectrum and you P-complete it. in a precise sense in this case, because the K-theory spectrum consists of all of the homotopy groups are finitely generated abelian groups, it does coincide with tensoring with ZP, or with just in each term P completing the K groups. Okay, so that's the main theorem. And let me just, okay, there's, yeah. So let me give a remark that's exactly related to this. So for prime to P information, then one has Henselian rigidity, or in this case, you could also use Dundas, Goodwillie, McCarthy. So specifically, if you look at the completion, the profinite completion away from P, which is telling you all the information for all other primes, that's just the same as what you get for the residue field FQ. And these were computed by Quillen. In fact, the K-theory of finite fields has no interesting Piatic information whatsoever. There's no P torsion in the K groups. And so that kind of splits the problem in general into two parts. One, the prime to P part, which is totally known by Quillen, and the orders of these groups are all known, of the K groups. And then the other is the more difficult Piatic part. Okay, that's the first remark. The second remark is something which really we were only able to prove after constructing this algorithm and running it on a bunch of examples. And we started to see an interesting pattern, and we were able to prove that pattern always holds. So specifically for I bigger than some bound, and it's a specific bound, that doesn't make sense. So times P to the n over E minus 1. So in this range, the even groups vanish. So H2 of Ci bullet is equal to 0. And of course, that Ci is K2I minus 2. Okay. So somewhat miraculously, there are non-even K groups for these rings, but they all start to vanish at some point. So this is called the even vanishing theorem. And there's also an important proposition so this theorem is also due to us. So there's also an important quotient theorem due to Engeltveit, at least in some cases, and then proved in a different way by us, which says that if you look at the orders of the groups, so these are finite abelian groups, and you look at this quotient, this is always equal to Q to the I n minus 1. Q again is the residue field, I is this weight, n is the power of the uniformizer we're killing. And together with this theorem, we get a corollary which says that for I bigger than that bound above, bigger than or equal to the bound above, well, this K group always vanishes. So this tells us that the order of K2I minus 1 OK mod pi to the n ZP is Q to the I n minus 1, no matter what. And that tells us that all orders are computable. Meaning, with finite time, one can figure out all of the orders of all of the k groups of any given OK mod pi to the n. Okay, why? Well, below this bound, you run our algorithm to compute each of these CIs and figure out what k2i minus 1 and k2i minus 2 is. Above that bound, all of the even groups vanish, and so you know the order of the odd group. Okay, and that's is it good for me to flip the boards? It's fine just to leave them. That's kind of what I was thinking.
Yeah, we've also got a question from Zim. Is the bound and the even vanishing here optimal?
No. So, yeah. The result does not depend only on those things, although the bound does. The question was, does the result depend only on I, E, and N? And the answer is no. So let me just say one more thing about the nature of this result. For Z mod 4, for example, one can compute all of the k groups, all of the orders. Okay. It has a single non-vanishing k group. Let me just get this correct. K2. And all other even k groups vanish. And so that tells you the orders of all of the groups. K3 Z mod 4 turns out to be isomorphic to Z mod 8 times Z mod 3. And then all of the other groups, 2i minus 1, we don't know the exact order, but we know that the primary part of it is Z mod 2 to the, it's a statement about the order, is 2 to the I, and the prime to 2 part of it is computed by Quillen and is cyclic of that size. As far as I know, this is the first commutative ring in which P is not 0, and that has some arithmetic interest, for which all of the orders of all of the k groups are known. Let me just say a little bit of history before I go in and tell you about the proofs, how the proof is going to work. So when n equals 1, that's the case of finite fields. That's due to Quillen. When n is less than or equal to e, that's the case of truncated polynomial rings. Fq adjoins z mod z to the n. That's the case when these rings happen to be characteristic P. And that's originally due to Hessel-Holt and Madsen using trace methods, and then later revisited, as we say nowadays, by Martin Spears using the new approach to cyclotomic spectra of Nicklaus and Schulze, and then more recently revisited again by Akil Matthew and then Yuri Salima for using techniques very similar in spirit to what we're going to do. In the non-characteristic P situation, classical homological algebra techniques had sufficed to get like K3 and K4. And that was basically it. That's what was known through the 90s. And then using THH and specifically filtered THH, Brun and Engeltveit had been able to get up to around 2p minus 2. They could compute up to degree 2p minus 2 for the k groups of rings like this. They focused on Z mod p to the n or truncated Witt vectors, and not this general OK mod pi to the n, so not the ramified case. And that was basically it. So this is the first method that can go beyond that. And so for p equals 2, you'll note that 2p minus 2 is 2. So this was the last group that was specifically known in that case. And this was in the literature, but it was actually incorrect in the literature. And so for Z mod 4, we've computed up to, say, I don't know, I forget, maybe K35 or so. And at some point it starts to get a little bit slow, but that's, quite a bit larger than K2. Okay. So sorry for a very brief history lesson, but I'm going to try to say as much as I can about the proof in the next 90 minutes as I can. Okay. Any questions before I start in on that? What was that? I'm sorry, yeah, I should have said that. The question is age 0 always 0? And that's a pretty crucial point. For I at least 1, age 0 is always 0. Yeah, so this first map is just injective. I guess I can write that down. That's pretty important. Okay. So now I'm going to pretty rapidly try to say something about how the proof goes. I have no idea how far we'll get. We're not going to get to the whole proof. You won't be surprised. There are some subtle questions about exactly in what generality some of the statements I'm going to say hold. Please don't ask those questions. I'm not going to answer them during this talk, but I'd be very happy to talk to them about them afterwards. They will all apply for the case of OK mod pi to the n. Okay, so that's all that's really relevant here. So so this part is called methods, and I'm hoping to even get to the algorithm to say something about that. And so throughout, unless otherwise specified, this is going to be about R equals OK mod pi to the n. And just I'm going to say 9 facts that are going into this and to try to explain what's happening as much as I can. So first of all is this first reduction that I mentioned. KR of OK mod pi to the n with ZP coefficients turns out to be isomorphic to TCR, the R homotopy group of topological cyclic homology, at least for non-negative R. And this can be proved in many ways, maybe classically, Dundas, Goodwillie, McCarthy, plus the result of the computation of Quillen of K-theory of finite fields. You could also appeal to the Henselian rigidity paper of Klaus and Matthew Morrow. Okay. So that's point A is already done. So what I've just observed is we can immediately reduce to a TC calculation from a K-theory calculation. Okay. Oh, right, I get to do this. Sorry, I don't have to go. Okay, so let's see if B can be quite as short. B, there's a filtration called the BMS2. Maybe BMS is more typical. The BMS filtration. It's a filtration on K-theory, or on TC, excuse me. It's a complete decreasing filtration on TC of a ring. Here, we can let R be quasi-syntamic, which is some sort of notion of a P completely LCI ring. And the important thing about this is the ith graded piece of this filtration is what's called this Piatic syntamic complex that I mentioned above, evaluated at R and shifted up by 2i, homologically shifted up by 2i. So, and of course, there's an associated spectral sequence coming from this filtration and converging to the TC groups, which are the K groups. So the name of the game now is to actually compute the syntamic cohomology. So I'll just call this, this is Piatic syntamic cohomology. So if we can compute these, we've computed TC and hence K-theory at least up to a spectral sequence. It'll turn out that that spectral sequence degenerates in our case. Maybe I should start here. Okay, C. What the heck are these Piatic syntamic complexes? I'm going to try to tell you this is the fiber of a map from a bunch of symbols to another bunch of symbols. And it's really an equalizer. It's the difference of a canonical map from here to here and a Frobenius map from there to there, as is kind of familiar from various approaches to TC as being a fiber of two maps from TC minus to TP, for example. And this is also for R quasi-syntamic. This was sort of first defined in BMS in the second Botmoro and Schulze paper. What are these objects? So prism R, this is the absolute prismatic homology. This is the ith Broglie, kiss, and twist. And I'm going to, which is behaving as a Tate twist in this context. Tate twist familiar from Étale cohomology. And then this refers to a Nygaard filtration to another filtration on this object. Okay, so we'll see what these are in a minute. Okay, well that's kind of a lot. More and more terms that maybe we don't know. So let me try to explain what all of these are. So that takes us to D, which is going to be a rapid mini course in prismatic homology. And it's specifically relative to delta rings, which is a slightly extended version of the theory that we introduce in our paper. And so first of all, I have to tell you what a delta ring is. So a delta ring is a commutative ring with a function. And I really mean a function, not a commutative ring A. And a function from A to itself, it's a set function, such that first of all, delta of 1 is 0, which is also delta of 0. Delta satisfies a certain formula for addition. And you'll note that despite the quotient, this has integral coefficients. And then it satisfies a certain formula with respect to multiplication as well. Where did this come from? You might reasonably ask. And the kind of point of this is that the operation phi of x, which is x to the p plus p delta x, is a ring endomorphism. It's now a ring map of A. It turns out you can check easily in 1 minute on paper, and is a lift of Frobenius. So A mod p has a canonical Frobenius endomorphism given by raising to p powers. And this is clearly a lift of that, because mod p, this term goes away. If in the case that A is p torsion free, then it's really equivalent data, because you could take a lift of Frobenius and then define delta x by x to the p, phi of x minus x to the p over p, when that makes sense. Okay, so that's what a delta ring is. So we're interested in these. An example of the delta ring is ZP itself with the identity Frobenius, and then the delta ring structure is whatever it is. That's a p torsion free ring. So what's a prism? So it's a pair, A comma I, where A is a delta ring, and I is a Cartier divisor, or the ideal of a Cartier divisor. in A such that, so it's a pair satisfying two conditions, such that first, A is derived, Pi complete. And second, sort of I, it's a Cartier divisor, so locally it's generated by a single non-zero divisor D, and delta D is a unit. So this is true locally. This is a purely, purely kind of algebraic notion, and so okay, so what now? So that's prisms. Here's prismatic homology. So A delta ring, R an A algebra. And we're interested in the following site, R over A prism. This is going to be the site of commutative diagrams. Like this. So here, this is a prism, and this is B bar is the prism modulo its defining ideal, and this should be a delta ring map, and this should commute. I want to make this a site, so I'd probably better take opposites, and additionally, I want to give this a topology, so I could give it the P completely faithfully flat topology if I want. Maybe R should be P. Well, okay, I said I'm not going to talk about any hypotheses for this. So this has a structure sheaf. The structure sheaf sends a diagram like this to B, this top right corner. So this turns out to be a sheaf of delta rings on this site. And the prismatic cohomology of R over A is the derived global sections on this site of this structure sheaf. And then maybe I might use prism bar R over A, which is the same thing, but I take O prism bar, which is just the structure sheaf that gives me B bar instead of B out. That's the Hodge-Tate locus. Okay, so now you all know what prismatic homology is. So that's defined some of the terms here. And I want to get as far as I sort of can in convincing you that this is a calculation that is possible to do. So far, this is super abstract. But there's several structural theorems that are known about it. So the Hodge-Tate comparison is the first one. I should say here I'm just requiring A to be a delta ring. That's not kind of how it's done in the original work. In Bott and Schultz, A is required itself to be a prism. And in the absolute case, that's kind of our definition, but where A is just ZP. So if A is ZP, which is a delta ring, then this recovers absolute prismatic homology. Okay. But let me just try to tell you as little as possible in order to believe that there's some algebraic approach here, which is that this Hodge-Tate cohomology. So here A will be a prism. So there's a conjugate filtration, an increasing conjugate filtration on the Hodge-Tate locus in the case that A is a prism. And the graded pieces of this conjugate filtration are computed in terms of differential forms. The derived exterior powers of the cotangent complex of R over A bar. And then there's a certain Broglie kiss and twist here, which in this case is easy to write down. For A bar modules, A bar Broglie kiss and twisted by 1 is just I mod I squared. So as an A bar module. So that tells you what this is. Now, the important thing that I want to say is if we're in the special case where R is a further quotient, so I take I and I quotient out by a regular sequence, R1 to RC. So this is a regular sequence in A bar. Well, then these, oh, and there's a shift, sorry. A cohomological shift. So if you do this cotangent complex calculation, it just turns out that, that these terms are all discrete. And so it implies that the Hodge-Tate cohomology of R over A in this special case is discrete, which doesn't look very cohomological. It's actually some discrete commutative ring. And that implies by completeness that prism R is discrete. Okay. Oh, do I go up here now? No. Okay, so what I've just said is that at least in some cases, for regular quotients, the resulting prismatic cohomology is actually discrete. And maybe I should have mentioned that like prism of A bar over A is A itself, just as that's kind of like the base of the prismatic theory. So the theory is discrete, and so there should, in this case, be a way of computing. So this theorem, sorry, hopefully I said this out loud. This is due to Bott and Schulze, not us. This should imply that there's some kind of algebraic way of computing this, this prismatic cohomology in this special case. And indeed, in that exact case, what you can say is that the prismatic cohomology of R over A is computed by a so-called prismatic envelope. So when A is actually orientable, so there's something you can say in the non-orientable case, but that doesn't matter for us. So in the special case that I is actually globally generated by a single non-zero divisor, then there's a specific algebraic construction you can make to compute the prismatic cohomology. And here, this is a ring you obtain by pure algebra. So this is A, and you adjoin some pure delta ring generators. So there's an algebra of delta rings, and there's a free algebra in delta rings. So you adjoin C free delta ring generators, and then you quotient out by the delta ideal generated by dAi minus Ri in the delta theoretic sense. And then you, sorry, let me try to raise that up a little bit. And then you Pi complete this. But the point is, this is pure algebra. Complicated algebra, perhaps, but it's just pure, playing around with polynomial rings. Okay, so let me try to. Okay, I'm going to skip exactly discussing the Broglie kiss and twists. Okay. So when did we start actually? When does this end?
About 10 minutes late, so.
7 minutes. Okay, perfect. So these Breuil-Kissen twists and Nygaard filtration that come up in the definition of this are also explicitly describable in this case of a prismatic envelope for one of these LCI quotients. Let me not say something about them, and instead let me say the strategy which reduces us to, so you don't get to see H. So let me say this main idea of Breuil-Kissen descent. This is sort of being used in a slightly different way than Breuil-Kissen twists here. Well, let me let AS be the Witt vectors of FQ, and then power series in variables Z0 through ZS. These are all delta rings where phi of Zi is Zi to the P, which you can sort of work out is the same as asking for delta of Zi to be 0. And each of these maps to OK mod pi to the n by sending all Zij's maybe to the uniformizer pi. So I can view us as being in the situation of trying to compute prismatic homology of this over this, and so the main idea is to look at a cosimplicial diagram. So ZP is the tote of this cosimplicial delta ring, where you insert the variables kind of in the usual way. This is like some completed Amatsur complex. And so what does that give you? So Breuil-Kissen descent refers to the fact that we can compute the absolute information from the relative information over these over these objects AIs. So the sort of theorem is that all of the pieces of information that we need are computable locally by descent. So for example, n more than or equal to I prism R is tote of n, sorry, and with a Breuil-Kissen twist, n more than or equal to I prism R Frobenius twisted by 1 I R over A bullet. So I look at each of these over this cosimplicial diagram, and I can compute this as the totalization of that. And then a similar statement for the total part, and then even a similar statement for the syntamic cohomology. So this is a tote of a version of syntamic cohomology for the relative situation. But now the upshot, like why does that really buy us something? The upshot is that, well, each of these, so I said send all Zij's to pi. This is actually a situation of prismatic cohomology over an ordinary prism, because inside here, inside the kernel, so is a factorization, there's a factorization AS bar to R, where here I'm viewing AS as a prism by looking at the ideal generated by E of Z0, where E is an Eisenstein polynomial. For OK. That's the first time somehow the number field itself comes into play. Very sorry, everyone. OK, so an Eisenstein polynomial is one like z to the e plus then p times something. And the only condition that is that P, you write the rest of this, and then P does not further divide this coefficient A0. Every ring of integers OK is the quotient of WK power series Z0 by an Eisenstein polynomial. And now the only difference is that we have several variables. But that's OK, because what happens is that in this picture, R is now AS, so that's WFQ power series Z0 through ZS, and it's then modded out by the ideal generated by E of Z0, and then I just need to equate all of the other variables, Z1 minus Z0, Z2 minus Z0, up to ZS minus Z0. And this is exactly one of our LCI quotients. And so that implies that the prismatic cohomology of R over AS is given by AS and then some this does not look quite right yet. I also have to quotient by Z0 to the N by some prismatic envelope. And so now, very briefly, what the strategy is.
Doesn't that ring just some quotient of power series on Z0 and you're setting all the other variables equal to Z0. So what's the point of having it?
Right, that's true for this. Okay, yeah. So the question is, why bother having all of these other variables here? Because we're just going to kill them. And that's very true. It doesn't change R by adding these variables, but it does change the prismatic cohomology of R. The prismatic cohomology of R over AS, this kind of complicated envelope construction still does see information from those other variables. That's kind of part of the, I guess that's part of the point, because here we're viewing this as prismatic cohomology over AS, not as over A0, the one with one generator. And that's important for our strategy of Breuil-Kissen descent. That's necessary for our strategy of Breuil-Kissen descent. Sorry. And then R is the quotient by the ideal. I'm sorry. So, okay, so just in 0 remaining minutes, let me say that. So now what's the strategy? So we have some purely algebraic approach to computing each term in this tote diagram. Okay, so one term at a time. And then there's two additional bits of information that help us out. First, we can use totally different methods to show that these terms are concentrated in a small range of degrees. So there's some finite cohomological dimension, which means we don't have to go very far out in this cosimplicial diagram to compute. In fact, we only need to go to s equals 0 and s equals 1. So that's part one. Part two is everything in sight has a filtration. R has the Piatic filtration, and this ring has the Z-atic filtration. And it turns out that we also don't need to go very high. This term, when we give it the filtration induced by the Piatic filtration on R, it just doesn't have high weight information. And that means that when we try to do these calculations, which are huge rings, we can restrict to some finitely generated ZP submodules of those and do the computation everywhere in each degree there. And there's still a bunch of subtle aspects for making that work algorithmically by computer, but it's possible. So I'll stop there.